So let me introduce you Axel Naumann. He's visiting us from CERN. He's part of the core team at CERN that develops the root toolkit and all the C++ and Python integration work that they're doing. So Axel, please introduce yourself a little bit deeper.
Yeah, no, that's already good enough. Thanks a lot. And thanks a lot for inviting me over. It's a pleasure to be here and talk a little bit about the funny things we do, which, you know, I would see them as not as relevant for companies like Google, but maybe I'm wrong, so we'll see. Let's give it a try. I'm going to talk today about how we use C++ in an interpreted world, actually, also, and the new interpreter that we came up with. And I'm going to talk a little bit about Python as well. So ideally, what I will cover during this half hour or something is C++ as it's used by CERN. I'll, of course, also talk about the LHC a little bit. Then the interpreter I was referring to is called clang. That will give you a good impression of a lot, but not exactly of everything. So CERN is a research lab. We really do just fundamental research, high-energy physics. We try to answer fundamental questions like, what is mass? We don't produce things except for knowledge. So it's just to satisfy our curiosity. CERN has been founded in the 50s. It's on the other side of Switzerland, near Geneva. And the main tool we have we use it as a giant microscope to see tiny things, is the Large Hadron Collider. What we do in there is we have a ring, and we send protons one way around and some protons the other way around, and then we let them collide at control points, and we measure what happens over there. I put a few of the numbers up. They are really very unique worldwide. We have an energy of 8 TeV. We have 2 Kelvin inside the magnets because we need them to be superconducting, which, by the way, also makes us one of the largest, if not the largest, consumer of helium of the world. And the whole ring is 27 kilometers long. It's huge. Now, because this is such an investment, of course, we try to make as good use of it as possible. And so we have about 10,000 users, 10,000 physicists, and several experiments at the LHC. This is what it looks like. It's beautiful down there. And that's the reason, of course, why we are there, right? We have the Alps, we have the lake, we have some green fields, and then what you don't see is the Jura, so it's fantastic. And then we came, and we had to put the ring somewhere. Luckily, we decided to put it below ground. So this is what it looks like. We have a few entrances to our tunnel, and then you see these caverns down there. That's where we put the detectors. Now, the detectors are giants. You can see the small people in front of this yellow platform. You can see that this is lots of heavy lifting that we have to do, but also tiny parts. I mean, all these small, intricate parts here this is one of the detectors, have to be built, right? And you can't order them. So this was all handmade. You also see a bit of the beam pipe here. The beams collide in the center of this detector. It's spectacular to see this yourself, and you might have a chance next year because we have to shut down the LHC for a year to do maintenance. So if you want, sign up in a few months, and you might get a tour down there. It's probably the last time, actually, that we open this up for the public. Okay, so that was CERN. Now let's switch to C++ a little bit. If you're a physicist, you learn C++ very early on. Because if you want to do data analysis, what this really means is you have to code. You immediately have to code and have to interface with your experiments libraries. That's how we do data analysis as high-energy physicists. The experiments libraries are giants. Maybe not in your environment, but for us, it's huge. We really notice the effect of gold a lot, for example, with gigs of libraries. We have enormous amounts of types, and we have about 50 million lines of code, C++ code. Not all in-house. We have a fair fraction of external dependencies, but a lot of that is actually developed in-house. And you ought to remember that we don't sell services or something. For us, computing is just something that gets us to where we actually want to go, namely physics. We do research, and we use computing just as a tool. I work as a member of the root development team, and root is one of these core ingredients that all the experiments share because they don't want to reinvent the wheel, and root is one of those wheels. We take the physicists and help them write when the data leaves the detector so that they can serialize the data, they can store it. Then we give them math tools at hand so that they can do statistical analysis. And then in the end, we even do the graphics part so that they can produce plots and publish them in their publications. We have a lot of users, 10,000 at CERN, 20,000 in total. We also have a few more unknown, and the reason is that we have a very unique collection type, something that is highly efficient if you have a huge amount of similar data, like our collision data. And for example, banks use it for stock markets and these kind of things. Root has an interpreter, so it's very easy to start it up for people. It's a small binary. And they then load their experiments code into root. And so they use root as a simple interface to the experiments code, to these giant libraries that I was talking about. This interpreter is now about 20 years old. It's called CINT, and we have a lot of experience with users interpreting C++ and CINT. And actually, these interpreters have a long history at CERN by themselves. About in the 70s, the first interpreters at CERN showed up because somebody was like, well, I just want to look at my data, and I want to rewrite a program and, I don't know, probably still punch cards, hand it over and then look at it, and then if I change my mind, want to look at something else, I have to reprogram again. No, I just want to fire it up, and then I want to enter what I actually want to look at. So to access data, the first interpreter was born. And then, of course, the first user said, hey, that's fantastic, but actually what I want to do is I want to do A plus B. So can you just add plus and minus and divide and multiply and so on? So simple expressions, that was the next step. Okay, what about, functions or something? Okay, so then came simple algorithms. And you can see where this goes, right? I mean, in the end, if you do this, then of course you want to prototype your algorithm, right? If you write an algorithm for the big experiment framework, then why don't you test drive it in the interpreter to see how it behaves? You optimize it, and then you put it into the giant framework. Okay, and now what really happens nowadays, the last step, is that people write their code in the interpreter, and then once they're happy, they put it back into the framework. And this is the main reason why we believe that interpreting C++ is important, because it gives you a way to develop your code in an interpreter interactively and have the same language as your compiled word. So since the old days, this is sort of the layout. We have these giant block of libraries and data, the official part. And then we have physicists who write their analysis code and who interface with the giant part using an interpreter. The current use is such that it's used as a code development environment. It's mainly used instead of just blinking and so on because it's so much faster, right? You can change the code, and within fractions of a second, you see the result. You don't have to go through all the build steps. And it's something very nice because even though you don't know the whole giant library, you can just peek into different corners. You can test drive code, test drive classes, see whether they behave the way you want. I think another reason why this really caught on at CERN is because if you write a physics analysis, you have an idea of an algorithm, you try it out, and it works, mostly. And then you try to refine it stepwise. So there's a lot of code change, see how that affects the outcome, and you go back and forth all the time. And that's supported, of course, by an interpreter. Now, given that we had CINT, we were really happy and lucky. But of course, when people want to do all fanciness with the interpreter, then with a homegrown interpreter, you reach the limits at some point. So we were looking for alternatives. And when clang and LLVM came around, then that was just amazing. It was a brilliant set of libraries to be used for, well, possibly be used for an interpreter. So clang is based on LLVM and clang, these C++ libraries. It's developed by a small team of people at CERN and at Fermilab in the US. And our main challenge was to map the concept of an interpreter to the concept of a compiler. This sounds like not a big deal. It is. It's a huge deal. And for all computer scientists out there, I understood from my dear colleague, the computer scientist, that we are actually not doing an interpreter because we don't interpret anything. We use JIT, we compile really natively. But for me, that's just a detail because it really feels like an interpreter. So the main thing we had to change was the understanding of what a translation unit is. A compiler has a translation unit as the full input it ever sees. And at the end of the input, the end of file, it does things. C++ requires things to happen at the end of the input. Now, we can't afford that. We have to do things at the end of each input. But the AST will grow. There will be more input. So some certain actions need to happen in between all of the input lines, and some we need to delay to all the end. So, for example, code gen needs to happen after each input. We want to be able to call all the functions that have been entered by the user. Something else that might not be that obvious is the fact that you cannot naturally use C++ at a prompt. Because there is no way that you can enter in a sane way code that is C++ in one global space, so to say. Let me explain you what I mean. Here we have int I equal 1 and sign of I++, okay? Now, that cannot stand on the global scope in C++, right? You've got to wrap it somehow. And I'll show you why we need to wrap it and why we need to extract declarations, why we need to find declarations versus expressions. So if we take the same input, what we do is we wrap it first of all, because that makes it legal C++. Clang can parse it and can tell us this part is a declaration, that part is an expression. So what we do then is we need to extract the the declaration, and put it onto global scope. Because otherwise, its lifetime is just inside the wrapping function, something we don't want, right? We want people, if they enter int I, they should be able to reference that I later on at later input lines. So it must become of static lifetime. So we do this on the AST level. There's no reason to do this on the textual level. We just extract the AST nodes and put them out. So then we are left with our wrapper function, which has only the expression. Of course, we need to call it, because that's what people expect, that the function gets called. But do people actually care about sign being called or not? No. They care about the outcome. They care about the result of that call to sign. So we use a hack that was invented for CINT, and that's fantastic. It's very simple. If you omit the trailing semicolon, then we will print the result of the last expression. And so that's what you get. Cling will print the result of sign using some magic that I'm not going to describe in detail here, but it works. So there are a lot of details which makes the whole thing ugly, but still working. One of the things is that global initializations are really tricky if you don't have a defined concept of a translation unit. Usually, you run your global initializers once when you start up your program, right? Here we can't do this. We have to do it step by step. When there's a new global, we have to initialize it. But we must not initialize all the globals that were already there, because otherwise we are going to reset their values. They might have been changed. On the contrary, for the destructors, we really need to collect everything and then run everything when cling dies. And something that is super evil is wrong code. If you enter wrong code, say our int I with a sign afterwards, and you misspell sign, then what people expect is that the whole thing goes away. The compiler forgets the whole input. So even the declaration of int I must be removed. Now, which compiler implements removal of AST node? None, obviously, because it's insane, right? It's highly inefficient. And so Clang doesn't do it either, but it allows us to tweak a few things, a few loopholes, and that's what we use. And so we successfully recover from errors like that. Okay, that was insane, but we are going yet a step further. We were able, with the alt interpreter, to open a file which contains serialized C++ objects and to just inject them into the current scope, the C++ scope. It's extremely handy if you interact with the compiler, with the interpreter. You open a file and you just want to see what's inside. You want to call a function on it. Now, that doesn't work with the compiler, right? Because this is not valid code. The compiler has no idea what the object in file really is. And it cannot determine this at compile time. Because it doesn't know, will it enter this part? What's the file name? What's inside the file? So all of that has to be done at runtime. The way we do it is we postpone the compilation of this part until runtime, until we know what's inside the file. So we use the compiler as a service, or as my friend, the computer scientists say, hey, that's just like a DLR, some dynamic language runtime, apparently. So the JIT that I was referring to already before is fantastic for us, not just because it gives us nice performance, and it does. The performance is amazing. But the real advantage is that it gives us ABI compatibility. This kills SWIG right there. Because we know how the target invokes functions. I mean, clang knows, right? Or LLVM. We don't have to take care of it. So we can immediately, just because of that, call into libraries, into shared libraries natively. So in this example here, let's look at the invocation of cling. You see that we switch it to C mode, and then we load a shared library in, which is libz, and then we pipe this code into cling. So here we declare a function, and then we call it. And you can see it just works like that. There is no wrapping involved. It's just native calls. Another part that is super essential for us is reflection. As you know, C++ has this weak point of not knowing what it's talking about. There's no runtime reflection. So we always had to generate a description of our types, just like you guys do with protobuf, for example, right? But now with the AST, there's no need for that anymore because the compiler knows it all. We can just query it. So we know the memory layout. We know where to stuff data at runtime. We know the target ABI, all these kind of things. And even better, we can annotate the AST. So we can put our own comments into the AST to help us with our serialization and all these things. I think cling, as it is already in a very usable state. It's really fun to toy with it. It does what you would expect to do, but we still want to drive it a little bit further. One of the main crucial parts that's missing is Clang's support for the Windows C++ ABI. Clang doesn't offer it, and as Clang doesn't offer it, we can't offer it either. It's actually LLVM and Clang. So this is something that we are really, really hoping to get and have fixed at some point in the near future. Something else is much easier, which is C++11. Because we use Clang as a front end, we will just inherit Clang's abilities to support C++. And features get added continuously. So I think this will just be fine, not an issue. Objective-C and C++ are not really a topic at CERN, but it's something that is also easy to add. We know that simple things can already be run in Objective-C and C++. OpenCL is the same thing. I believe it's mostly implemented in Clang, so it should be naturally supported in Clang as well. And then, of course, you can go crazy and just implement Link or whatever front end you like. So given how fantastic Clang is, of course, you all want to know, how do we get it? Well, here it is. You can check it out. It's rather stable, so don't expect a lot of API changes. It's really, really small. It's frustrating to see how much work we put in, and the more work we put in, the smaller it seems to become. It really works everywhere where LVM and its JIT work, so notably not Windows. And we deliver it as a standalone binary, which allows you to play with it. But I think most importantly, we deliver a few libraries, sort of modular libraries that allow you to interface with it and embed it in any way you want. Oh yeah, and the important part here, I guess, is that it's not GPL or something, but we use the same license as Clang and LVM. So something similar to MIT. Okay, so given that I had such a mixed bag of topics to present here, I allowed myself to have several conclusions, I think 3 in total. So let's start with the first one, the interpreter language. Actually, not yet the conclusion. So right, Python. Oh, I almost forgot about Python. Yes, so here comes the Python part. So we talked about C++, interpreting C++. And of course, we all know that this is awkward, and so people use Python for interpreting, right? It's far more compact. It's a little bit more casual coding than C++. The way we did it for root is by implementing a standalone tool, a bridge between Python and C++, which is called PIROOT. It's invented by Wim Labreise, who's out there in the net. If you look for Python and C++, it's him all the time. So the bridge works like this. You can do calls in either direction. You can call Python from C++, and you can call C++ from Python. And it maps concepts. So it understands that if something implements an iterator interface in C++, it should be iterable in Python as well. Dictionaries the same way. The best thing are its internals, which are not visible. That's the point of having it internal, right? It's not stub-based. We don't need to pre-process the headers to generate information. There is nothing at compile time that is forced to be run to be able to use it within Python. Instead, we just use reflection, which we already have, and we continue to have with Clang in an even better way. So dynamically, we build the knowledge, we add the functions to the Python objects that are available in C++. It's really performant because it caches a lot, and it uses some form of object annotation on the Python side to be able to remember certain properties that it will use when bridging the language barriers. No. No. It uses regular Python libraries, actually. So the C interface to the regular Python library. Yeah, so it's built on top. It's not implementing a Python interpreter or something like that. Yes. Oh, yeah, exactly. Yes. Sorry. Yes. Right. Sorry. Right. So now the question is, of course, well, maybe it's not the question, but for me, this is one of the big topics: is what do we want to interpret? Do we want to interpret C++, or do we want to interpret Python? Now, I understand, of course, the drive to write Python because it's so much simpler than writing C++. It's actually frighteningly simple to write 1 million lines of code Python. But what we see then is that, once you have all this complex algorithm Python, are you really going to rewrite in C++ the whole thing and verify that it's giving the same results? Maybe next week, right? So we end up with a whole load of of Python that is not as performant as we would want it to be. So for me, this is really an issue. I still love this sentence that I heard somewhere about the I/O performance in Python. Okay, so here comes the conclusion, the first part. Interpreters. So for us at CERN, interpreters are more than just a command line interface or something like that. They are really a different way of interfacing with giant libraries, with a lot of libraries, and a different way of writing code. Much more direct feedback, explorative coding. The key for having interpreters work properly is reflection data. And I really, really hope that we will get it into C++ at some point. It helps us with dynamic binding for interpreters. It helps us with serialization and with anything dynamic like plugins and whatnot. Languages are always a matter of taste, and so this slide is highly, my personal opinion. Nevertheless, I think that the languages we have chosen still limit us. CERN did a transition from Fortran to C++ in the 90s, and transitioning 10,000 people to C++ was a huge effort, especially when these people are physicists. They're not computer scientists, right? And we did so successfully, which means that C++ is really amazing. And it works for novices as well. Novices can pick up C++. They do understand how to write their analysis. On the other hand, it's easily possible to write C++ code that is completely ununderstandable, definitely also for novices. So that's a danger. With Python, of course, the problem is that it's difficult to migrate the code out of Python into a more performant version. And so what we see now is that we have code, massive amounts of code, in either language, and we have nowhere to go because there is no other language that inherently is able to interface with C++. Think of pound include myheader.h. There's no other language which allows you to do that. If you think Fortran or C, that was possible. That was a nice migration path, right? But nowadays, we have to use things like SWIG or so to survive. So that's the sad slide. Here comes the happy one, clang. I think what I'm trying to say here is that you can trust us. We have a lot of experience with novice users, with C++, and with interpreters. And all of that ended up in clang. And we are really happy with the product. It's really worth a try. Having clang in LLVM is amazing. It really is a game changer in the way you write parsers. You do anything with code, actually. And because it's fun and stable, I think it's a good time to start looking at it. And because I know that the really only thing that's convincing people is a demo, I will have a demo. But I'm not going to do it myself. Instead, I found a demo by some random guy that I don't personally know. He picked up clang in the early days. He found it amazing. He likes Qt apparently as well. So he used it to showcase how you develop Qt with clang. I find that amazing. It's on YouTube. So I understand that this talk is recorded as well and put into YouTube. So for the geekiness of it, we will have recursive YouTube here. But I don't trust your wireless connection, so I downloaded it. So this is what it is. The window here to the left is an interface to clang. It's just a Qt layer on top of it. So what I think Thomas Garr is his name, what he's doing here is he's loading code into clang, header files, declarations. Okay, .l does that. Before he linked clang already, apparently with the Qt libraries. So all the symbols are there. He's now just declaring things to clang. And here we have the first variable that he created, and he called show on that variable. And you see how it pops up, right? The window popped up. He's moving it. This is live, okay? It's just, the code is there. Of course, that's boring. We just have a widget now. So he wants to do things with it now. And especially Qt, which is very visual, right, benefits from having an interactive programming because he immediately see what's happening. So now he's going to define some layout and inject a button there. So let's see what happens. He's declaring it. And, well, now the object is created. Now he's adding the widget. And ideally, there it is. Right? We haven't written clang for that. That's just the side effect, right? You can do whatever you want with it. It's just C++. Okay, so we have clang as the backend, and clang is a proper C++ compiler. So hey, why not use signal slot, proper preprocessor constructs, you know? Okay, so he's connecting signal slot, this button to window hiding, and whoa, it works, and it works repeatedly. So he's enjoying it so much, he's now doing it 3 times. Right, so now he's changing the size as well, because he wants to have it more, I don't know, suitable. Shows it, and it still works. So I think this gives you a very good impression of how dynamic development can be, how visual, how closely your feedback is if you use an interpreter for code development. So thanks a lot for coming by. Thank you. Yes.
So, this CERN summer student in 2000, so I remember that there was C++ class and all the systems. there's all these libraries in Fortran 90. We're never going to switch to C++. So there was some fundamental things like that. So, I mean, of course, for me as a computer scientist, it was kind of strange that people would willingly subject themselves to old languages that never been operated. But it was actually, apparently, that was the attitude that were able to, you guys were able to make that switch. I believe it's far from obvious to bring about such a change. And that's what my question is about. How do you, when somebody like a summer student or a new researcher comes there, he's not going to be used to use, well, maybe he learns C++ and stuff, but he's not going to be used to your interpreter. It might have like loadings in particular and stuff. So how do you educate? Do you have a training program, tutorials, or things so that you can make sure that people can pick up not C++, but specifically things? Is there some guidance?
So many different parts, that question. So, yes, sure. So the question is, how do we educate novices how to use Clang? If I can summarize it like this. And so first of all, we try to make Clang as natural as possible. So the .l you saw here is actually not needed. You can just pound include the headers as well. That's also an option. But I think the main answer is that we have 10,000 physicists out there. And these summer students, for example, will have a supervisor. And this supervisor will have written hours and hours and hours of code with root and interpreters. So they know how this works. And that's actually how it spreads. That makes it very easy for us. We are only 7 people in the development team. You know, we can't educate the world. I mean, no, all 10,000 physicists. But of course, it makes it also very dangerous because we have no idea what they tell these people. And, you know, sometimes we get these funny things where we see code like, who wrote that? Everybody's using it. God. So, you know, it's ups and downs. But yeah, it spreads. You know, if it's a good tool, something that makes sense, is easy to use, I think then you don't need a lot of introduction. For C++, of course, that's different. We still have lessons of C++. It's still one of the biggest headaches that we have, that summer students who just stay there for a few months need to learn C++. That's costing them a considerable amount of time. Yeah, that's life, right? I mean, that's the language we chose, and it would be the same with any other language, presumably. Yes?
Do you have support for dynamic introspection with MATLAB? Or are they on the rapid probability?
Right. So the question is, do we have support for dynamic introspection, you said, right?
Yeah, just like looking at your API and looking at the objects of the methods.
Right. We do. We have several, actually, which is painful. And we're going to reduce that to one. There's one in root, which is the mother of all, because it's used by serialization and whatnot. And so you can ask any object that is used, I mean, that's known to root, basically, that is of a type that has been declared to root. You can ask it for its type, for its members, calling signatures. You can call dynamically through the reflection interface any functions of these objects. So yeah, all of that is there.
That is root and out of the
No, we have it implicit. We have it deco. You process the line, you get the AST deco, which is part of the AST, so you can basically get whatever you want there. And even you can change dynamically, and you can add declarations and expression of that, and then you can reuse it.
Right. So the answer by Vasil was yes. It's part of Cling and Clang. I mean, we have a whole freaking compiler and JIT in the backend, right? So of course, yes, we can use anything we want. Yeah, it's all there.
So you have completion.
Ha! Do you have completion on the prompt? Yes, we do, but only in root and not the way we want it to be. So Clang has a feature for completion, and we want to use it. But the problem is that it's intrusive with the code, with the string buffer containing the code. So we don't know yet what we're going to do with that, because in principle we would have to again revert AST nodes that the user might have typed, then pressing tab, and then it's actually not what I want, and then back up, and so that's kind of messy. But we'll find a solution for that. That's the plan. So we have it only in root for now. Yes.
Is there a way to walk into an existing function somewhere where they can get access to the target? So if I write how instantiate incorporate a hill get talk that we can actually access target?
Well, yes. This gives me more time to think. So the question is, given a binary context, I believe, which declares, for example, variables and functions, can you access that through clang, right? That's your question. And I think the answer is yes, but you have to declare it. LLVM, the debugger based on LLVM, does funny things by calling debug symbols, for example, for that. So that would be an option, but we don't implement that. Unless you declare it, it's not going to be available. Yes?
How do you handle failure? So for instance, from the gentleman who wrote that code had passed a null pointer to queue blocks layout. What happens I guess you're not fetching the interpreter. So how is it handled?
So the question is, how do you handle failure, crashes, segmentation violations, these kind of things within clang? Very good topic, very difficult topic to answer because everybody wants it differently. So if you use clang in a bigger framework, then of course you don't want clang to capture anything. You want it to be passed through unless it actually crashes. In that case, you want it to be buffered or something like that. So all of that is up for discussion, right? But the main point is we can only do so much. If there is a crash, a hard C++ crash, then we can try to recover using the usual things, signal handlers, yada, yada. But, I mean, the state afterwards is going to be unusable anyway. So we were actually thinking of moving all of the interpreter out into a separate environment. But then in the end, you don't gain anything because the whole environment, the whole context is in that different process. And, okay, it crashes, you would nevertheless have to restart from scratch, right? You can't just replay everything. So that is basically unsolved. We can handle a few things, but if you have a crash, you have a crash. Yes?
What is the workflow like using this? Do people kind of play around in the interpreter and then copy and paste bits into the text file, or do you have an IDE that kind of integrates the permanent version of the playground? Or I could even see something like a Lisp machines where you have like an environment that gets saved.
Yes. Yeah, all of these are really fantastic. So the question is, do you have an IDE which makes use of the interpreter such that input becomes a source file, for example? We have put a little bit of time into creating at least an editor that interfaces with the interpreter. But, given the scope of things we have to deal with, we are not going to be able to implement something like that. There is actually an editor out there, I think it's called Scintilla or something like that, that has been, I don't know whether it still does, but it has been using Scint as an interpreter, under the hood. And so, yes, I mean, this is definitely something that will make sense, and especially with Clang and its new abilities, that's something that would be very tempting to have. But I don't think we'll be able to implement something like that, especially as you'll never be able to convince all physicists to not use VI, not use Emacs, not use Eclipse, these kind of things. You know how it is, right? I mean, yeah.
Better phrase the question, is anybody working on like an Emacs mode, for example?
So the question is anybody working on Emacs mode, which uses Clang as an inferior shell? Not that I'm aware of. No. Yes, sad. Huh? But I think there's something with Emacs and Clang. I think there was a module, right? But,
So here at Google, we typically we have an environment that has access to source code, but when we're running a server, and suppose that for some reason I wanted to be able to go into that server and run the interpreter and do all the nice things that I was able to do on my desktop machine. However, it would mean, since you need access to the types and everything, that the source has to be somehow accessible, right? Do you have any support for this? Is it a use case that you have to deal with? Or is it purely run on the developer machine or something?
Right. Let me try to repeat the question because that also make sure that I understood it well. So the question is, you have a server which runs some code, and what about enabling the server to have an interpreter interface so that you can log on and interactively play with the server, basically. Is that about right? Or so there are a few things. Whenever I hear server and interpreter, I go, whoa, especially C++, right? I mean, don't, really. The second part is, yes. The whole thing is meant to be used in a production environment as well. So it's not just interactive. And given that we have these gigs of libraries out there, we're not going to have all the source code all the time. The plan that we have is that we build something that is called modules, clang modules, for each of the parts of the frameworks. They're basically partial PCHs that you can inject into the AST. You load them into the AST. Fantastic, really. I really, really hope that this will end up in C++ at some point, if it's feasible. So by that, we don't have to publish the source code. We can just put the PCHs, the modules somewhere and load them in dynamically, actually on demand even, because when the library gets loaded, then we load the library's module so that we make reflection data available. Yes?
In the root context, the analysis code is sent to all the servers.
Yes.
So every root process can interpret code, call the API, call cling or call CINT with a C file, with a file code. So for data analysis, we have kind of text that how to do it is system and the scientist prototype is C++, and then he submits it to the job and the C++ 5% and interpret all the servers. So and then if it's finished, you get the result back and change it to the analysis code and submit it again, so all the servers stay waiting for the next sprint. So you can very fast prototype even in this. So basically every process via API can do execute.
Right. So we have a just to repeat that to the microphone. We have a batch system based interpreter. So your local front end actually means that you submit the code you enter to a whole cluster of nodes, which then works away on the input. And yes, if you write wrong code, then you will have to restart this cluster once in a while. This happens. It's all dynamic. It's your process anyway, exactly. So no questions on Python and C++? You're all happy, huh? Okay. Okay. Yes?
Maybe related. Are there any features besides introspection that you, I guess, been wanting in C++ that maybe are useful in an interactive mode that might not be useful?
The question is, are there more features than reflection that we would want to see in C++ that are useful for an interpreter, correct?
Seems like a very verbose language full of special symbols.
I think, the syntax of C++ is sort of limiting its usability as an interpreted language, by design. But that said, C++ 11 goes a long way in simplifying what you have to type. So I think this is a step into the right direction. And from what I see, one of the main arguments with new features is always, look, people, these 20 lines of code will collapse to just 2. We need this feature, and that's the right approach. That makes perfect sense. So I think really reflection is one of the key features. There are more features like the uncertainty about the target layout. None of that is available. You don't know how the target is going to put things into memory, how a call actually works. These kind of things that would be very nice to have as well. Yeah. Yes.
How about one function rule? Is the way to redefine the definitions?
Excellent question. So the question is, C++ enforces that one definition rule. how do you handle that? Can you handle that? Can you have multiple definitions in the interpreter? So especially when you prototype code, you write something and you change your mind because it's not the right thing and you change it. But then that changed function has exactly the same name as the function before. You want it to be replaced, the old one, right? So our alt interpreter had actually the notion of unloading code and reloading code. So it forgot parts of the AST. The reason why I didn't mention that here is because we haven't implemented it yet. But this is absolutely the goal. I mean, the whole point of prototyping is exactly that you can live change code and, modify the contents of functions and so on. This is closely coupled to error recovery, as you can imagine, because also there we have to forget parts of the AST. We have to add a little bit on top of that because we even have to make globals, so values, forgotten. We need to uncode gen, so to say. So it's a little bit tricky, but I think we'll manage because we sort of know how to do this in CINT. We have the experience from CINT, so it should be possible. Does that answer it? Yes?
About the Python interface.
Yes.
So you said that the mapping between C++ and Python was completely dynamic. So can you do something like loading a header file with the definition of your C++ template and then start calling methods that directly from Python?
The question is, I was claiming that the C++ Python interface is completely dynamic. Now let me test you. What if I load a header file which contains a template? Can I actually call the functions? Now with CINT, you could not with our alt interpreter because we needed template instantiations. Now that we have a compiler and a JIT in the backend, we can do this dynamically. And so the answer will shortly be, yes, absolutely. You can just call the function because we will generate the symbol automatically and it will be made available to Python.